Welcome to Finite Element Methods. Today we'll be discussing the 1D interpolation elastic bar. Today, for the first time, we'll be covering finite elements per se. So we're going to be extending the ideas of approximation methods for the strong from Galerkin, weak from Galerkin, and Rayleigh Ritz. Finally, we're going to be applying finite elements. Now, when we studied the spring elements and the truss elements, they didn't require differential equations, and that's what makes it different in the sense that we're now really applying the idea of approximating solution over a domain and then uh, formulating the finite element method. In my book, I'm basically covered several chapters. Now I'll be covering chapter 4 and 5. There are three approximation methods that we've discussed: the strong from Galerkin, the weak from Galerkin, and the Rayleigh Ritz method. The weak from Galerkin is very nice. You start with a governing equation, you multiply by weighted residual, and then you integrate it by parts to weaken the continuity requirements. That way, the approximation function you select can be sufficiently differentiable, but it does not going to require a higher order polynomial like the strong from Galerkin does. Secondly, the weak form Galerkin only requires essential boundary conditions be satisfied. The Rayleigh-Ritz method is a great convenient method if the function of the problem exists. If a problem, if the functional exists, then you can go ahead and use this approach. And both of these, the weak form Galerkin and Rayleigh-Ritz, form the basis of the finite element method. And so, what I'll be talking today about is um, that the weak form Galerkin tends to be more general than the Rayleigh-Ritz method because it can be applied to non-conservative systems, where in Rayleigh-Ritz method, you need a functional. So a functional means that you probably have a conservative system. Approximation functions are chosen and the residual errors are made orthogonal to the basis functions in the weak form Galerkin. And then you integrate by parts. And the idea is to automatically satisfy the natural boundary conditions in the weak formulation and and then try to make your approximation function just satisfy the essential boundary conditions. So what are the finite element steps? Is to derive the partial differential equations of the physics problem, formulate the general behavior of an element, derive the weak form of the PDE or the ODE. And so that first you have to come up with the PDE, right? And the second step is to come up with the weak form of the PDE, and then use an approximate function over the subdomain of interest. And that's going to allow us to determine the limit stiffness matrix and the force vector. We will then discretize the domain of the structure into elements. That's the next step. And then we will assemble the stiffness matrix and force vectors. Then from there, we can now impose the boundary conditions. We can then solve the algebraic system of equations and then post-process the results for the variables of interest. What is very cool is that the way I've been teaching this course is such that we've already done parts of this. So we've done parts of how to do the weak form. We've done how to assemble a stiffness matrix, how to do the boundary conditions, how to do all these steps. But the new thing today is how to approximate the function over an element. That's the new thing we'll be discussing today. So if I consider the example problem of a bar, elastic bar that has an axial load applied, and I have an axial load applied at several points in the domain. The loads are applied are at various axial stations, as you can see here. And in another example that you have here is a beam. Now I have a transverse load with a simply supported here and here, a roller support here, a roller support here, and you can see there's several boundary conditions along this bar beam. In both cases, it will be better if I can approximate the solution over a domain such that I don't have those discontinuities you see here. For example, I have load here, load there, load there. Maybe I can create an element that ends here, another element that goes from here to here, another one from here to here, another one from here to here. Similarly, it would be nice to have an element that ends here, another one that ends here, and one that ends there. So three elements for this one. Um, so what is the idea here? What is the idea behind what we're trying to do? If I were to use a polynomial approximation to try to approximate a solution over the whole domain for the axial bar and over the whole beam domain, it's going to be a little bit tough because um, I had to somehow have really good solutions in areas where you have those discontinuities, and maybe you have to have a very high order polynomial to make that happen. So we're going to use polynomials as approximation functions, as most finite element codes are really using polynomials. And they're convenient, they're easily differentiable, and can be integrated very easily. But the three limitations with this approach is that for polynomials of low order, like cubic quadratic, that approach may work well. But as the order is increased to prove accuracy, it can also result in an unacceptable solution. So I can go, okay, yeah, I can go to seventh order to try to get a nice solution for this problem. But the higher the order of different, the higher order polynomial you select, the little bit harder you can get physical answers. The unknown coefficients don't have physical meanings. When I see these coefficients C naught, C1, C2, they're just mathematical coefficients. They have no meaning whatsoever. So that's another disadvantage with the approach I've been teaching with the weak form Galerkin and Rayleigh Ritz. Unknown coefficients, then you have the situation where if I had an element here and another element here, this element here is going to have unknown coefficients for a polynomial that approximates the solution over this domain. This element is going to have unknown coefficients for a polynomial that goes over this domain. But there's no easy way to relate the coefficients across this boundary. We know that the deflections across this boundary where the rotor is such that the deflection should be equal. Well, I don't have the ability that easily. There's no easy way to do that if I select a polynomial like this. So the idea then is, can we divide the domain into subdomains and use lower order piecewise polynomials over each subdomain? And so if I'm able to divide this domain into smaller domains and then use lower order polynomials for each of these pieces, that might be more tractable. And then if I have a way of making my nodal unknowns, my coefficients that are unknown, into nodal unknowns, making those the ones that are unknown that way, then perhaps I have something closer to what I need. So why we don't go and see what we could do to get there? Okay. Yeah. So have you ever used Excel in the past and you have 3 or 4 data points and you want to fit a polynomial? If you select a very high order polynomial like 8 or 9, have you seen that you get some oscillations sometimes that don't? You know that the structure does not respond that way. So yeah, I encourage you to try it. Go to Excel, enter some data points, and try to fit it with a ninth order polynomial. I think you're going to see some oscillations occur sometimes. But that's not the point. If I have, it's just not tractable. Can I really use a polynomial to solve a whole aircraft? I can't. I have too many. The geometry is very complex. I have loads applied in different places. It's not straightforward. So what I need is to divide the domain into subdomains, elements, and then go from there. And that's what we're going to do today. So first, I want to now look at this problem. So I have the 1D bar, and I know what the essential boundary conditions are. We know that any boundary conditions specified on U is an essential boundary conditions. And we know this because when I derive the weak form of a elastic bar and I integrated by parts, I got this expression where V was a weight function. And I can look at this V, and anytime I see V, I make a mental note and say, okay, that's kind of U. And anything specified in U becomes your essential boundary condition. So this is what you're going to use to determine what are the essential boundary conditions of the problem. So if I divide the domain into four subdomains, here I have divided like this, so because that's where the loads are applied. Um, I think everybody agrees here that the elements are not breaking apart. We know that. So unless we have cracking across these element boundaries, if this if I don't specify the deflection U across the boundary, then I'm going to have a crack. Obviously, the deflection here at this node must be equal to the deflection at this node. Otherwise, I'm going to have a crack right there. Same here, same here. So therefore, across element boundaries, U is specified in the sense that it must be continuous across the element boundary. The U has to be the same left and right. Otherwise, this is going to break apart as you see in this picture. It has to be. It has to be in that manner. Otherwise, we will have a crack. And so the essential boundary conditions are a good clue. It tells you what to pay attention to when I go across element boundaries. When we study beams, you're going to see that for order Bernoulli beam, The slope is very important as well. So consider a one-dimensional bar subjected to distributed load Qx, and then I have a deflection Ux. I'm going to divide this domain into 1, 2, 3, 4 pieces and 5 nodes. And my goal is to use our goal, because we're a team, is to use the finite element process to determine U. That's what I want to do. We will first approximate the local element behavior with a linear polynomial such as xi. So here you can see I have nodal values x1. So this is what I've done. I have these nodes x1. I have these nodes at x1, x2, x3, x4, x5. I'm going to show them here in this x-axis, x1, x2, x3, x4, x5. So those are the nodes where the nodes are. And u are the values at that node. And I'm making them up for illustration purposes. So u1 is a nodal value at x1, u2 is a nodal value at x2, and so forth. We were going to approximate the local element behavior with a linear polynomial. So the idea is I'm going to use a linear polynomial. I can use a quadratic polynomial such that xi are the nodal positions and the deflection ui are the unknown deflections. In such a manner, when I plug in this x into u, I get ui. If I plug x1, I get u1. If I plug x2, I get u2. So all I've done right now is to show you a kind of like top level view of what we're trying to accomplish. We will use an interpolation function ux between xi and xj to approximate the behavior across these coordinates. So what I want to do, I want to take the approximate. So if I had an exact solution that transverses points, right? A linear polynomial is an approximation over that element, right? Because I divided this element, this domain into 4 elements, 1, 2, 3, 4 elements. And I can see that here I have 1, 2, 3, 4 elements, and u is a deflection of x1, u2 is a deflection of x2, and so forth. So I definitely want to find a way of interpolating the deflection between x1 and x2, x2 and x3, and so forth. And you can see here that this is my exact solution. The exact solution looks like this, but I'm going to approximate a solution like this. So it's going to be linear in between. And again, it's an approximation, right? We're going to use this interpolation approximation function in the Rayleigh Ritz and Galerkin. And this is beneficial because the unknown coefficients. What are the unknown coefficients here? Let's think about that. The unknown coefficients, I don't know what the deflections are. But if I pretend that these are the unknown values, which are the ones I really want to find, because I want to know how the elastic bar deflects, then it would be beneficial if I wrote my approximation function so they're a function just of these deflections at these nodes. So how do I approximate? How do I do that? So let's select an element E, a generic element E with nodes I and J, and the node I has a coordinate of xi, the node J has a coordinate xj, and the deflection node I is ui, the deflection xj is uj. And you can see here I have the element E and a generic element E, which has those coordinates. And what I want to do is I'm going to use a linear approximation across this element. And a linear approximation is the lowest order element I can select, polynomial I can select. And the reason is because is sufficiently differentiable. I can put a linear approximation here and I get a constant. So that works. It can be done. We can select a linear approximation. So if I chose a linear approximation, I have u tilde at x for this element E, and I put a E there because that approximation is true for this element. I get C naught plus C1x. We know that this must be ui. We know that deflection at xi is ui. We know that. So I'll plug it in there. We know that the deflection xj right here is uj, right? So I have two equations. And I want this C naught and C1 to be in terms of these nodal quantities, because these are the unknowns of the problem. It would be nice if these coefficients were written in that manner. So very quickly, I can do that. I can try to solve it. I can solve for C1, I can solve for C0. And notice how I can plug in xi minus xj to be minus LE. And what I get now is a utila for element E is the approximation here on the right. Let's see if this works out. If the element length is LE and the coordinates are xi and xj, let's see if this approximation function does what we think it should do. So let's say u tilde at xi. Let's see what happens. When I put u tilde at xi, xj minus xi is le, so I get ui. So u tilde at xi is ui. So far, so good. But if I put xi here, this goes to 0. Perfect. U tilde at xi is ui, and that's exactly what I need. If I look back, the deflection u at xi is ui, and that's exactly what I get with this expression. Let's look at x equals xj. When I do that, this goes to 0, and this goes to le. So uj times 1 equals this, and that makes sense. The deflection at xj is uj. So this is a very good approximation function, but notice how I made my unknown coefficients to be the nodal values, and they do have physical meaning. They're the deflections of the problem. That's what makes this so cool. Okay, we're able to find a way of relating my approximation function so they become a function of the nodal values that are unknown, because those are the quantities I'm interested in. So, so given that we're clear about what this is about, I have a suitable approximation over my element, right? So let me go back to show you what we've done. We've taken this domain divided into 4 elements, and there are 5 nodes. And in typical weak form Galerkin, you're going to have a polynomial approximation that has unknown coefficients that must satisfy essential boundary conditions. And note how in weak form Galerkin, we're able to approximate solution over the whole domain, but that's not advantageous. Not always advantageous, because I may have loads applied, point loads, and stuff like that. Let's divide the domain into subdomains, and then let's approximate a solution over a single domain, and then go from there. And what I'm showing you here is this real solution to the problem. And instead, what I'm going to do is approximate solution using linear interpolation. You can see that looks like a line. This is more curved. So if I use a linear interpolation and approximate solution over this domain, the unknowns are ui and uj, here u2 and u3. And to accomplish that, I showed you how we could get there. And this is the approximation function I came up with. Very nice so far. That has taken us some time to explain, but I think we're getting there. So if the approximation function u tilde is this much, and I already showed you that that works out for the conditions of the problem, and the weak form Galerkin is this much, and we developed that in previous lecture, in the weak form Galerkin lecture, lecture number 6, we developed how this looks like for elastic bar. We started with EA U prime prime plus Q or minus Q equals 0. And that's where this came from. We integrated by parts once, and this is what we got. We got these extra boundary conditions as well. Notice how the element approximation selected satisfies the essential boundary condition for that element. Why, when I'm looking at a single element, looking at a single element, the boundary conditions I have for the element are essential. Why? Because the deflections here and the deflections here must follow the deflections of the neighboring element. This deflection here has to follow the neighboring element deflection. This element here has to follow the neighboring element deflection. So that's forcing my deflection to have to satisfy the essential boundary conditions across the element, so that I can satisfy the fact that across elements the deflections are the same. So that's forcing the issue there. So I showed you 2 methods of getting there: the weak form Galerkin or using the Rayleigh Ritz. Both methods give you the same answer. In lecture number 7, I showed you how minimization of pi results in the weak form. We showed that. The beautiful thing about this that's quite amazing is that the essential boundary conditions are automatically met. because the nodal unknowns are imposed as the unknown coefficients. We can check that. If I plug in at xi, I plug in xi here, this becomes LE and this goes to 0. So u tilde at xi gives me ui. Is working out. Finally, the basis functions are linearly independent and form a complete set. So if I look at this phi1, this phi1, according to our Rayleigh Ritz and Weak Form Galerkin approximations, if you look at phi1 and phi2, you cannot write phi1 in terms of phi2. They're different in nature. So it is kind of convenient to plot them and see what's going on. Now, when it comes to finite elements, it pays off to write everything down into very simple equations. So here are the unknown coefficients. I'm approximating the solution over a domain, over the element E. And you can see here UIE is the nodal value UI. This is the nodal value UJ. And note how this is the shape function. We're going to call this basis functions that I was calling phi1 and phi2. We'll call it shape functions. I will show you why. So let's call this NI and this NJ. And notice how these are the phis that we had before. I can write this in vector format. So I can write this NI and NJ as a row, and then UI and UJ as a column. That's very convenient later on when I apply finite elements. I'll call this M bold, and I'll call this column vector D bold, which contains the unknown coefficients, the unknown nodal values. But again, U tilde here is approximation over the element domain E. That makes total sense. This is the polynomial approximation for this value or this function U. Um, and that's what I plan to then substitute into the weak form here in the Rayleigh Ritz. But I want to put in a tractable manner first. Now notice how Ni is this right here, Nj is this right here. You can see that there, Ni is this, Nj is that. And so these Ni and Nj are the phi1s and phi2s and phi3s we discussed prior, but we're going to use n. This is the convention that in the finite element world we use. These n's are the basis functions in Rayleigh Ritz, but they're also called shape functions because they have shapes. Let's look at Ni, for example. Ni starts at a value of 1. So let's plug in xi here, and you see xj minus xi is the element length. Element length divided by element length is 1. So you can see this height here is 1. And then notice how when I go to xj, this function goes to 0. So this drops to 0. Now when I look at nj, it starts at 0. When I put xi here, it gets 0. And then it goes to 1 at xj. You can see xj minus xi is the element length. Element length divided by element length is 1. So this is very interesting because we can now use this idea to derive shape functions in the future. I'll be discussing that in future lectures. But there's something beautiful about this that needs to be discussed, that I want to really discuss, is that the shape functions satisfy two important properties that become very convenient in our formulations. The first um, important property is that they satisfy something called a Chronicle Delta. In other words, the shape function corresponding to a node I. So if I have a shape function corresponding to node I, that shape function will be 0 everywhere else. You can see here that Ni is 1 at this node, but Ni is 0 at this node. You can see that Nj, which is the shape function that corresponds to this node, J, is going to be, um, well, you can see here that um, Nj is 1 here, but is 0 here. So when I say it corresponds, when I look at this, Ni goes with Ui. So Ni is a shape function corresponding to Ui. It's a coefficient to Ui. And Nj is a coefficient to Uj, just like when we had the polynomial approximations before. Okay. So this is what we have. That's called the Chronicle Delta property. It's going to be very advantageous later to have that property. Um, Another cool thing about that is because this shape function is one at this node and zero everywhere else, you know for sure that this approximation function will always be equal to the nodal value at that particular node of interest. So that's going to come up a few times, and I think you're going to see that advantage. The other cool thing about this second property is that if you add two shape functions, they'll be equal to one. You can see if I add shape function for node I and shape function for node j, if I add them up, I get one. And that's actually a very necessary condition. Let me explain why. Say the whole element moves rigid body to the right. The whole element moves at the same time to the right. Well, then let's call that movement let's call the movement of to the right a value a. So the whole thing moved a. This node moved to the right a. This moved to the node an amount a. So if I plug in a and a here, so for the deflection UI I plug it a, and I UG I plug in a, U tilde becomes a times ani plus nj. I need ani plus nj to be 1 so that I can claim that the deflections at every point in within that domain is a. This node moves A, this node moves A, everywhere in between moves A. So that has to be the case, that Ni plus Nj is 1. Otherwise, things are not going to work out. Um, the shift functions, and I have a whole chapter in my book on how to deal with piecewise approximations. And that's a way of going about this. And it really gets you there. One could define something called global shift functions, but I'm not going to cover this because it's in my book extensively. The bottom line is that if you have a shape function for element 2 and shape functions for element 3, what I want to show you is that if this shape function and this shape function add up, and they add up so that it looks like a triangle, like this little piece here is this piece, and and then I have a piece here, which is this piece. And at node 3, you get a full value of 1 at this node 3. But that's if you want to look at everything from a global perspective. Instead, what I'm going to do, I'm going to formulate the element behavior by approximate solution over the subdomain, just looking at this domain. And if you're interested in how I did it by looking at global shape functions, which is using this method, go ahead and read my book so you can get that perspective. But for now, what I'm going to do is approximate solution over this element, which is what I've been doing. And I showed you how U tilde can be approximated over this domain by making a function of unknown quantities that are representatives of the deflections at this node I and node J. I made this in bold. I made this D bold because it's going to be very helpful as I move forward. So the governing equation for an axial bar was this much. I have the element E, which has a length LE with a load distributed load applied P. I have a nodal deflection UI to the right, a nodal deflection UJ to the right. At this point, I can also apply load PI and load PJ. And if I look at the weak form of the problem that we derived starting from this equation, I multiply this equation, and that's an error, no V there. I multiply this equation by V. And when I multiply this equation by V, EAU prime plus P without the V, I multiply the whole thing by V and integrate by part once. We demonstrated already in lecture 6 that this is the weak form of the problem, where V were the weight functions, right? So the weak form Galerkin for an element is this much. We already covered that. I'm just repeating this equation in the next slide. That's all I've done. And now all I have to do, like in Rayleigh Ritz in weak form Galerkin, was to substitute the approximation U tilde into this equation. That's all I have to do. And then for the V's, I have to select the basis functions. We'll discuss that in a second. But when I plug in U tilde, notice how I have to take these derivatives. That derivative U respect to X is required. So if I take the derivative U of respect to x, I get the derivative of this respect to x, the derivative of this respect to x, but I don't have anything to do here because these are coefficients and they're constants. I don't know them, but I had to find them. So I know I have to calculate that derivative, so that's why I did it here, so you can see that we need to do that. And notice how I can call this whole thing B bold. That's fine. I'm just calling it that. And notice how this column vector is D bold, the same one as I had there. Nothing fancy so far. I did this calculation because I know that I'm going to have to plug in U prime. And so let me just do the calculation now. So for equation number one, right? So how many unknowns I have? I have two unknowns, which is the nodal values ui and uj. So I should have two equations I have to write. The first equation, but with v selected as the first basis function, which is ni, and v selected as nj for the second equation. So I did that here. You can see that there. First equation, ni. Second equation, nj for v. Now you can see here that it's the same thing I have. I have EA, right? EA is there. You can see that there. And then for U prime, I converted that to B bold because these are the U prime is a derivative, which I calculated here. That's B bold. Then I have the deflate. I have this D bold that I cannot forget. So that's that. And then for V, I have to select NI for the first term for phi one. So V is derivative of NI respect to X minus P times NIX. And then when I plug it in here, NI, NJ, so for V, I'm going to select NI. But NI at node J is 0. We know that because of the Chronicle Delta property. While NI at node I is 1. So I get PI alone, which is what you see there, minus PI. And then for this V here inside the integral, weak form Galerkin, the weak form, I have P times Ni. Because for, again, how does the weak form Galerkin works? You formulate the weak form Galerkin. For U, you substitute the U tilde, the approximate solution. And then for V, you select Ni for the first equation and Nj for the second equation. That's all I've done. It's basically plugging what we just talked about. So these are two equations. Now notice how I can make everything even more compact. This column vector, I can put this in a vector, and you can see how this Ni and Nj derivatives of those with respect to x. This column vector is the same vector as this one, but is transposed. So then I can write this as B bold transpose. See that? This B bold transpose, and this B bold is a 2 by 1, while B bold is a 1 by 2. So I should get a 2 by 2 matrix, which makes sense because I have two unknowns, UI and UJ. Notice how here I have P, and I'm putting this on the right hand side of the equation. And notice how D bold, I'm sorry, let me go back here. Notice I put D bold outside of the integral because D bold is not a function of x, it's an unknown quantity at a node, specific node. It does not depend on x. I have this P there, as you can see, and then this against a column vector, and that column vector is this vector but transposed. So P times N bold transpose plus P bold, because for the first equation I have PI, and for the second equation I have PJ. So that's PI and PJ there. So note how for the weak form Galerkin, we substituted V for N bold transpose. And it's going to work out every time. If you do that, it's going to make your life simpler. So we're going to go ahead and evaluate these integrals. And now what I'm going to ask you to do is that instead of watching the show, that at home, I hope you're writing everything out and that you're stopping and deriving yourself. Because if you don't, it's going to be an uphill battle. So you want to make sure you're able to derive it yourself. So I have Ni and Nj. One of the things I have to calculate here is B bold. You see that there. So let's calculate B bold. B bold is this. I know that derivative of Ni respect to x, I can calculate that. That's minus 1 over LE. I can do that. Derivative of Ni respect to x, that's basically, yeah, so that will be 1 over LE. And you can see that I'm doing that here. This is B bold transpose, so that's a column vector. While here I have a row vector, so that's just that in there. And just multiply everything out. On the left-hand side, I get this equation. Yeah, so this is what I get. If we assume that the cross-sectional area modulus are constant, EA can come outside of the integral. And then notice how the integral of something that looks like this, where L is the element length has no bearing on what dx is. It's a constant relative to x. So this integral really here goes from xi to xj, but just of dx. That's it. And the integral of xi to xj of dx is just the element length. So the element length LE gets multiplied by this matrix here. So that's going to end up being EALE, 1 minus 1 minus 1, 1. The column vector here is UI and UJ. And I can evaluate the concentrated force here and the consistent element force here. Notice how this is the same derivation I derived using the equilibrium equations in lecture number 2 and 3. So that's an exciting moment that we're seeing here. Very exciting moment that I think you should pause and reflect upon. If I use the Rayleigh Ritz method, you're going to end up with something very similar. Here, you plug in u tilde. So this was the Rayleigh Ritz, the functional we got. We want to minimize that relative to the unknown coefficients, and the unknown coefficients are ui and uj. And there's an error here that u, the approximation function, should be ni prime ui plus nj prime uj, and that's squared. This should be uj. So this is squared dx minus the integral q, and then you have this u deflection that's ni ui plus nj uj, again another error. And then I have minus pj uj minus pi ui. That's the functional we got last time when we derived it. But I'm plugging in the approximation function now. Since I have it, why not just plug it in and see what happens? What I see, notice here is when I evaluate my approximation function at uxj, I should get 1, right? I should get uj, which is what you see there. And then the deflection value at xi should give me ui. So you can see here that I get this expression here on the screen. To find the unknown deflections ui and uj, I have to take the derivative of pi with respect to ui and set it to 0. Take the derivative of pi with respect to uj and set it to 0. Two equations, two unknowns. So if I just rewrote everything in the previous page, but here, this for general element E, right? You can see that taking these derivatives can take time. So there's a more easy and clever way of doing it. I already told you that I can write this equation as the one here. You tell me if that makes sense. So u prime, I can just put u prime transpose here. EA can go here, and then u prime can go here. If I multiply this, I get the same thing as EA u prime squared. This is makes sense because u prime is a transpose. Is the transpose of a scalar quantity is a quantity itself, and so I'm not doing anything fancy. U prime transpose is the same thing as your u prime. So u prime times u prime is u prime squared. That's that. So nothing fancy there. But this is a trick that's very useful. So now I do this trick, and now that I know u prime, I know u prime from here. I showed you that u prime is b bold d bold, where d bold is the unknown coefficients. So for u prime, I'll plug in b bold d bold, and for u prime here, I'll plug in b bold d bold. For u, I have to substitute the fact that that's m bold times d bold. That's going to end up being m bold transpose d bold transpose. And then I have this, but this can be written as d bold transpose times b bold, since d bold contains ui and uj, and p bold contains pi and pj. So that this is correct. That's also called the dot product of two vectors. That's really what we have there in this expression. Okay. So, so here you have dx. That's an error. This is not supposed to be dA, it's dx. We did it in the Rayleigh Ritz lecture, lecture 7. You should be able to see that there. So that's an error on my end. That's dx and that's dx. And if you wonder how went from this integral to this integral, is because that was supposed to be dx, so that's dx. And then u has to be plugged in for m bold d bold because that's what u is. So if we go back to what the approximation function is, we had stated earlier how u tilde is m bold d bold. But for these equations to make sense, any sense, we have to have transpose. Otherwise, it's not going to work out. Uh, and yeah, so that makes sense. So then I have also these terms, which is d bold transpose p bold. So that's that. Okay, so step by step, this I now have to minimize this. And notice how I have d bold outside, which are the nodal unknowns. And I already showed you, and in my book, I showed the proof of this, and I showed you this earlier for the spring formulation, how the minimization of the total potential energy, when you have a situation like this, if we were to use linear algebra, we can demonstrate that minimization of a quadratic function that looks like this is going to be such that if I take the partial of s respect to d, one of the d cancels out. So the d transpose cancels out, and this 1.5 disappears. So it leads to this. So if I were to apply this idea to what we got, what I will do if I want to minimize this respect to d bold is to delete d bold everywhere. I see it. So transpose, delete, delete, delete. And this one, I'll remove the 1.5. And when I do that, I get this minimization. Now notice how this matches what I got with a weak form Galerkin. That's what I got with a weak form Galerkin, the same thing. So the weak form and Galerkin and the Rayleigh Ritz are mathematically connected, and it's actually a mathematical miracle that they're connected at all. Because one of them is based on energy principles, the other one is starting from the equilibrium equations themselves. The weak form Galerkin starts from the equilibrium equations, multiplies it by the weight function, integrates it by part to develop the weak form, and that's how we formulate the element. While for Rayleigh Ritz, I start with the functional. The functional comes from the potential energy of the system. In my book, I show you how to turn I show you how to turn a weak form of the problem into a functional, but it's out of scope for what we're trying to do here. But you're welcome to go and check those aspects of the book. Here I give you an example. If you don't believe me, go ahead and try it at home. A simple example of two variables that are unknown. Just multiply yourself and take that derivative here. You will see that get kd equals q when you go through that process. Therefore, with both methods, I got the same element formulation. Beautifully done. Both the Rayleigh Ritz weak form Galerkin give the same formulation I got also in the when I developed the whole thing for an elastic bar for the spring element even. If you recall, we derived the same equations prior, but now we got the same answers we got previously using the Rayleigh Ritz and the weak form Galerkin. So let's look at an example. So I have a 1D bar linear shift function, and this has a distribution of loading like this, 3 elements, and then I have a transverse deflection, and I have a fixed node here. So I have a degree of freedom 0 here, 1, 2, and 3, 3 deflections. Load applied on this end. EA and L are constant. The element length is this length L divided by 3. So all I have to do is calculate this integral k bold, which I already derived the k bold earlier, that formula there. And yeah, I just multiply everything out and I get the stiffness matrix for a single element that's generic. For one of the elements that's generic, since every single element has the same size, then L is L over 3. And you can see here that everything works out very nice. And that's the stiffness matrix for the problem. So, so then we go ahead and continue. Now I have to calculate this integral, right? And Ni was xj minus x divided by Le, and Nj was x minus xi over Le. And what I have there really is this column vector. I know Ni and Nj. I know the formulas for those. So all I've done is plug that in. And the integral from xi to xj for generic element E, since all of them have the same distributed load, that integral is easy to calculate. And when you're done doing it, you're going to get q naught Le divided by 2, q naught Le divided by 2. It makes sense that you get half. So say that this for generic element E, right? So say that's element 2 here. Then what is the distributed load? The effective force is q naught times Le, and I'm putting half on node 1 and half in node 2. That's really what's happening. But because Le is a third of the element length L, of the total bar length L, then Le divided by 3 results in Q naught L divided by 6. It's just because one element is a third of the size, and that's why you see that here. So yeah, that's what you see there. I applied a load Q naught, and half of it went to the left and half went to the right, which is kind of cool to see happening automatically. Now I'm set. I have 3 elements. I have the code numbers set. 0 because it's fixed. 1, 2, and 3. For element 1, I have code number 0, 1. For element 2, I have code number 1, 2. For element 3, I have code numbers 2, 3. And so here you can see how we work it all out. Element 1, 2, and 3. I should have 3 degrees of freedom because those are free to move. So it's a 3 by 3. And then just populate this, searching for 1 and 1. Search for that and see where you can find commonalities. Global forces also need to be assembled. Here you can see how I have an assembly going on. Use the same thing, the code numbers, to figure that out and to figure how to add them up. The concentrated forces are easy. Node number 3 is the only one that has a load applied to the right, and that's that. So the total load applied then is this. And all you have to do now is solve for the deflections D1, D2, and D3. Because if I have this column vector, I know the stiffness matrix. Then all I have to do is invert the stiffness matrix, multiply by the forces to get the deflections. Example 2, finite element for 1D bar. So I have this tapered column. The modulus is this much. The thickness of the plate is 1 inch. We want to use 2 finite elements and basically solve the problem. And it's a self-weight problem, so we're going to say that we have some sort of density. And so now I go ahead and construct the finite element model for this problem. So I have two elements. I divided the domain into 2 elements. And I was sensical about how I divided the elements. Notice how I divided the elements. I did it in a very specific way. I also divided the length by 2, so 12 and 12 inch. I also have a mid load applied at 100 pounds. So I'm being very, very specific on how I do that. I also decided to model each of these sections as the average cross section for that particular section I divided the domain into. So constant cross section here and here. So for element 1, I have nodes 1 and 2 connected, and for element 2, the node 2 and 3 are connected. Okay, so now I can calculate the integral. And I actually decided to calculate the exact stiffness matrix for an element that has varying cross section. In fact, you can see that here. So for element 1, I have 0 to 12. B bold was calculated as this, so that doesn't change. The element length is 12, so that's why it's 12 squared. The area, the cross-section area is changing according to this function, okay? And you can determine that function from the geometry. I'll let you figure that out. You can see it works out. At x equals 0, you get 6 inches here, and the depth is 1, so you get a 6-inch area. So at this here, you get that. Halfway is 12 inch, so you have to multiply 12 times 0.125. And when you do this calculation, you will see that you get the width here. And then if you plug in 24 in this equation, you get 3. 6 minus 3 is 3. And you can see here you get 3 inches. Times 1 is a cross-sectional area, so it works out. So just go ahead and integrate this, and when you do that, you get the K1 for element 1 is this much. For element 2, it's the same process, but now I integrate from 12 to 24, since the element goes from 12 to 24. And now, same formula, and this is what I get for stiffness matrix for element 2. Now, I have a body force. So the body force is rho times area, like gravity, and I know what area is. I know what density is. It's constant. It can come outside of the integral. M bold is known. We know what Ni and Nj are. They're here. Xj is 12 for element 1. Xi is 0 because it's at the fixed end here. Xi is 0 and Xj is 12. The element length is 12, so you can plug all that in here. And then you integrate the whole thing, and you get that the force vector for element 1 is this much. For element 2, you get this much. Again, now the integral goes from 12 to 24 because I'm looking at this element here, which goes from 12 to 24. And this is the force I get. You may ask me, how is this even correct? Well, rho times density, right? So density times volume is mass, and you can see here that A times dx is volume. So that's what's going on here. We're integrating over x. Area is known, the formula is known. So now I can assemble the global stiffness matrix because I have element number 1, element number 2. I have the connectivity matrix. I can now go to assemble K, and I can now assemble F. F is 9.36. You can see that there. This one here comes from this one plus that one. You can check that when you do a nodal connectivity. But I don't want to repeat that process because you already know how to do that. And finally, for the third node, I get 5.96. It does not combine with anything. And then if you recall from the statement of the problem, I'm applying 1,000 pounds to node number 2. So I applied to 100 pounds at node number 2. Nothing at the very end because it's nothing being applied there. And at the fixed end, we don't know what the reaction force is. So I can then cross out the first row and the first column. And I notice here how the deflection U1 is 0 at the left, at the top end where it's fixed. Remember, this is not the one we're fixing it here. So all I have to do is solve for U2 and U3 from this equation. And that's easy to solve using Mathematica or MATLAB. Once I know U2 and U3, plug it back into this equation and multiply the first row times the first column to get R1. And you can see here, I've done that. Once I got U2 and U3, I multiplied that row by that column, and I was able to get the value for R1, which is minus 130 pounds. You can do a free body diagram just to verify your results. You know there's a reaction force at that end, which is what I'm trying to calculate. And you can calculate the total, basically the total amount of weight this is producing on this piece. and this extra 100 pounds. And when you do that, you get 130 pounds, which is what I got with finite elements. Now that I know the deflections, I can calculate stresses. Remember that stress equals modulus times strain, but strain in our problem is the derivative of deflection with respect to x, and I know that's b bold d bold for element 1. So I can calculate this very easily, and I get a constant stress of 23 psi. For element 2, I get a constant stress of 1.59 psi, which makes sense. I should have less stress in the bottom element, while the top element should have higher stress because it's pulling more load. It's pulling the load from the element below. And this is the analytical solution. If you're interested, you can plot here the analytical solution and the finite element solution, very similar, but off because we didn't divide the element the domain into a lot of elements. Note there's a slope discontinuity here, but that's fine. But the deflections were continuous, so that's good news. It worked out. The finite element solution does not produce exact solution even at the nodes, but this could be improved by increasing the number of elements or using higher order elements. The stress field is expected to be constant in each element, and the finite element solution for stresses tends to be less accurate compared to the finite element displacements. And that makes sense because I have a variation of deflection that's linear over the element, but the stress is a derivative of that approximation that's linear. So that makes sense. I should get a stress that's constant. You can see here the stress is off from the analytical solution. Every element is supposed to be able to represent the rigid body motion. We already talked about that. So this node moves A, this node moves A, then A can be factored out, and this is 1. So therefore, every element is able to represent this rigid body motion, and I showed you that this is the case for this problem. So if this moves on amount A, this moves on amount A, every point in between should move the same amount, and you can see that that happens. Doesn't matter what value of x you select. This element allows you also to represent a constant strain. And so if you assume that the deflection looks like this, the strain becomes something like constant. So the displacement interpolation allows for a constant strain rate to be represented by this model. Completeness is all about rigid body modes, constant strain rates, and convergence is to ensure that as you increase the number of elements, you will approach the exact solution. What are the steps in the finite element method then? Formulate the weighted residual based on the weak form. Integrate by parts. Reduce the order of differentiation, and then apply the natural boundary conditions. Discretize the domain into elements. Use piecewise polynomials to interpolate, and then derive the Galerkin finite element equations. Then assemble a system together using the connectivity matrix, and then solve the algebraic system of equations. Then post-process all your results. So that shows you how the finite element formulation is done for a 1D problem. We'll be showing how to do higher order interpolation next week in the next lecture. I apologize. So with that said, thank you for listening, and we'll continue our coverage in finite elements. It's an exciting moment because we're making the transition now from approximate methods that only work for simplistic problems to a more generic approach that can solve very complicated problems that may arise in structural mechanics, heat transfer, or any other area of expertise.